Ever since the developments of the first thermometers in the early 1700s, scientists around the globe became engrossed in finding the limits of temperature. The thermometer was an improvement upon its predecessor, the thermoscope, invented in 1596 by Galileo Galilei. Both instruments were exceptional at measuring temperature, but the edge the thermometer had over the thermoscope was the addition of a scale. The first scales came independently from two places at once, one from Danish astronomer Ole Romer and the other from English physicist Isaac Newton. Romer's scale took two reference points, the boiling point of water and the freezing point of salt water, and divided the space between the 2 points into 60 evenly spaced degrees. Newton simultaneously also took two reference points, with 0 degrees being the freezing point of water and 12 degrees being the temperature of the human body. It wasn't until 1724, though, that a scale would be invented that would eventually spring into widespread use by a Dutch-Polish physicist named Daniel Fahrenheit. At the same time of the invention of these scales, a French physicist by the name of Guillaume Amonton was doing a different kind of research with temperature. Rather than attempting to make his own scale, he was looking for the theoretical limit of temperature, which he called infinite cold, the minimum temperature possible to be achieved. From his research, he found that when a gas is cooled down, it pushes back on a liquid with less force than when it is warm. He called this property of gas springiness and extrapolated to a hypothetical lower extreme temperature in which a gas would lose all of its springiness. Amonton was the pioneer of research into absolute zero and would be the first of a few scientists working to find an infinite cold over the next 100 years. In 1802, French chemist Joseph-Louis Gay-Lussac published work that related the temperature of a gas to the volume of space it occupies. Due to the progression of technology, Gay-Lussac was able to work with multiple types of gas independently, such as oxygen, nitrogen, and hydrogen, as opposed to a general air supply being available to Amonton. When he published his work in 1802, however, he cited previous unpublished work of French scientist Jacques Charles from the year 1787. Charles had previously filled 5 balloons with the same volume of different gases, then raised the temperature of them to 80 degrees Celsius, and found that all balloons increased in volume by the same amount. From this, Charles established the following relationship, and because of this citation by Gay-Lussac in his 1802 paper, this relationship came to be known as Charles's Law. The importance of Charles's Law in finding absolute zero, though, came from extrapolating this relationship to the extreme. Charles noticed, while determining the temperature-volume relationship, that for every increase or decrease of 1 degree Celsius from 0 degrees, the volume of the air would increase or decrease by approximately 1 out of 273 of the volume of air at 0 degrees. Gay-Lussac expanded on this relationship in his publication and cited that, in theory, the volume of a gas would reach zero at approximately negative 266.66 degrees Celsius. Although this is a pretty close estimation to the calculated value of absolute zero today, Gay-Lussac made it clear in his paper that Charles's Law is not applicable at low temperatures due to the fact that at extremely low temperatures, these gases would become liquid and no longer would be subject to gas laws. To get to absolute zero, it would take an entirely different fundamental theory, and this would come in 1848 at the hands of British theoretical physicist by the name of William Thomson. Thomson was a graduate of Cambridge University, earning his Bachelor of Arts in 1845 at the age of 21. After his studies, Thomson moved to Paris to work under Henri Victor Regnault to gain experimental experience to compound with his theoretical education. The very next year, in 1846, the chair of natural philosophy at the University of Glasgow became vacant, and Thomson's father, a professor at Glasgow, campaigned heavily for his son to fill the seat, which he ultimately did at the young age of 22. Thomson was heavily influenced by the potential for a theory of everything, in which all energy, matter, and forces could be unified under one fundamental framework of the universe. This, coupled with the discoveries of James Prescott Joule regarding heat, led to Thomson conducting most of his work in the then budding field of thermodynamics. He turned his attention to infinite cold in 1848 and published a paper entitled "On an Absolute Thermometric Scale Founded on Carnot's Theory of the Motive Power of Heat." In this paper, Thomson deviated from using a specific substance, such as water, as a reference point for setting a temperature scale, and rather used what is called the Carnot cycle, and set up a scale based on its thermodynamic properties. Thomson stated in his paper that the ratio of work to heat in the Carnot cycle depends on temperature. To set his units of measurement, Thomson wrote that a unit of heat descending from a body A at a temperature T of this scale to a body B at another temperature would give out the same mechanical effect, whatever be the number. This way, Thomson's temperature scale was independent of material and rather dependent on thermodynamics. However, this 1848 scale did not work to Thomson's expectations, for at around the same time, experiments were being done by Thomson's former mentor Regnault on saturated steam at temperatures between 0 degrees Celsius and 230 degrees Celsius. Thomson found that his theoretical calculations did not match Regnault's experimental data, so he went back to the drawing board and published a second paper in 1854, stating that, quote, "The numerical measure of temperature shall be not founded on the expansion of air at a particular pressure, but shall be simply the mechanical equivalent of the thermal unit divided by Carnot's function." Upon making this adjustment and setting the difference between the freezing point and boiling point of water to be 100 degrees, Thomson's scale, at the time of release called the absolute Celsius scale, made its official entrance into the world of temperature, along with the first accurate calculation of absolute zero at negative 273 degrees Celsius. Thomson was known for many more things than creating the absolute temperature scale, for he was a massive figure in thermodynamics. Many things today are named after him, such as the Joule-Thomson effect, but most of these things are listed under a different name, a name he received much later in his life. Thomson was ennobled in 1892, taking the name Baron Kelvin, named after the River Kelvin, which flows near his former laboratory at Glasgow. The story of absolute zero spans more than a century, and the idea of an absolute zero existed long before Kelvin, thanks to the work of early pioneers such as Amonton, Charles, and Gay-Lussac. The actual calculated value of it was still unknown, though, until Kelvin laid his hands upon the subject, and the scale he invented based upon it is now the most widely used scale in science, as it measures absolute physical properties of the universe, independent of the subject matter being studied. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time period. Thank you for watching, and I will see you in the next video.